you will be solving. So continue. So when we speak of drying, that refers to the removal of a relatively small amount that is of water from any material. Water is usually removed as water vapor by air. So the water content of the material is being removed through the use of warm air. Now, may also refer to the removal not only of water but other organic liquids such as benzene from solids. Now, usually it is the last step in a series of operations in the manufacturing process. And this last step is usually carried out before packaging or dispatch. Now, the purpose, let me just have this class. Okay, and I will stop sharing and I'll share again because there's this something that every time I admit somebody, it comes out. So drying is carried out to reduce the cost of transport because of course of the lesser weight to handle and to make the material more suitable for handling, as for example, the powdered soft, the dye stuffs, and even the fertilizers, which I can't imagine if they have the amount of moisture more than what is specified for the packaging. Of course, there's a tendency for this particular powdered stuff to to go into lumps. Now, to provide also definite properties such as, for example, maintaining the free-flowing nature of powdered substances, and to remove moisture which may otherwise lead to corrosion. So water will lead to corrosion if it is being if the material is being passed through or transported to the use of pipes. So the presence of water will lead to corrosion. One example for this, the removal of moisture in gaseous fuels. So in the drying of gaseous fuels or in benzene prior to chlorination. So excess water has to be removed in this case. Now, when we speak of moisture of a material, it could be either in the form of bound moisture or free moisture. So when we speak of bound moisture, this is water retained so that it exerts a vapor pressure less than that of free water at the same temperature. Now, such water may be retained in small capillaries or it's only adsorbed on surfaces, so it's not absorbed but rather only on the surface, or as a solution in cell walls. Now, when you speak of free moisture, this is water which is in excess of equilibrium moisture content. So anything that is in excess of this is what we call as free moisture. Now, let's go back to the definition of humidity because we're going to use this particular concept again when we solve problems now related to dryers. So when we speak of humidity, it is the mass of water per unit mass of dry air. And if expressed in terms of partial pressure of water vapor, that would be partial pressure of water vapor over the partial pressure of dry air. So as you can see here, you have the total pressure, and from that we subtract the partial pressure of water vapor, meaning our denominator here refers to the partial pressure of dry air, and as such that is our humidity. Now, the humidity of saturated air in most references is represented by H with the subscript O. Now, this is the humidity of air when it is saturated with water vapor, meaning it contains already the maximum amount of water that it can hold for the given condition. The air in this particular condition is then in equilibrium with the water that it is holding. That's the maximum water content that it has for a given temperature and pressure. Now, as for percentage humidity, so that would be our humidity here, the H that we have defined here, divided by the humidity at saturation. So that's our percentage humidity. Now, we also have what we call percent relative humidity. Now, in some reference books, in the case of Colson, it's represented as capital letter R. That is, if you're using Colson, if you're using it as a reference, this one is represented as R. So this is the partial pressure of water vapor in air over the vapor pressure of water at the same temperature. So take note, class, that the numerator is partial pressure, whereas the denominator is vapor pressure at the indicated temperature. So these two are very different. When we speak of partial pressure, it's just the pressure caused by one component in a given mixture. In this case, the mixture of water vapor and air. But when we speak of vapor pressure, that's the pressure that the vapor of such a substance is exerting at the particular temperature indicated. And this vapor pressure actually can be read from property charts in section 2 of your handbook. As long as you're given the temperature, you can have this value presented here in the formula for percent relative humidity, or you can just simply substitute it in this formula. Now, when we speak of humid volume, actually, it's just the opposite of the density of your air-water vapor mixture based on the unit. So it's the reciprocal of its density. So in terms of its definition, it's the volume of the unit mass of dry air and its associated vapor. So I have said it's already a mixture of water vapor and air. Then under ideal conditions, if this one is impossible for you to determine or hard to read from the psychrometric chart, because actually what we have in the psychrometric chart is also the specific volume, then you can solve this particular humid volume based on this formula. So you can see here that everything are constants except for the temperature. So all you have to do is substitute the temperature, class, and the humidity. You have here the humidity. Then you will be able to get the humid volume of the mixture of gas, of your air and water vapor in that sense. So given the humidity and the temperature, you need not have it read from the psychrometric chart, because using the formula is much more accurate, of course, than having it read from the psychrometric chart. So that's in the case of the humid volume, or the specific volume, that is. Now, as for definitions that are important, so let's review some. So when we speak of saturated volume, it is the volume of unit mass of dry air together with the water vapor required to saturate it. So that's the saturated volume. Now, the humid heat, actually, I have presented this already in the psychrometric processes set of slides. It's just the CP of the mixture of water vapor and air. Based on its definition, it is the heat required to raise the unit mass of dry air and its associated water vapor by 1 degree Kelvin at constant pressure. Or it could be determined using this formula, class, that is in this particular formula, the resulting unit is in SI. So the unit that you will of course have to use here for your humidity is also in SI. Nonetheless, if you're using the units here in English, since they have both, they have similar units, let's say kilogram per kilogram or pound mass per pound mass, then it's not necessary that you also have your humidity here in terms of SI units. It would be the same if you're going to convert it anyhow from English to SI. So this is your formula for the humid heat of a mixture of water vapor and air given its humidity. So it's 1 plus 1.88 times the humidity of that air. Now, the dew point is the temperature at which condensation will first occur in air when it is cooled. So this is normally measured in the lab during experiments, as I have already told you in the previous discussion, in the case of the formation of the condensed water vapor on a particular plate, if this is conducted in an experiment setup. Now, as for wet bulb temperature, if a stream of air is passed rapidly over a water surface, now vaporization occurs, provided the temperature of the water is above the dew point of the air. Now, the temperature of the water in this case falls and heat flows from the air to water. Since, of course, water will be at a lesser temperature, the tendency, since air is hotter, the flow of heat will be from air to water. If the surface is sufficiently small for the condition of air to change inappreciably, and if the velocity is in excess of about 5 meters per second, the water reaches the wet bulb temperature. In some texts or references, it's represented as theta with the subscript W. In our case, we can represent it still as T sub W, wet bulb temperature at equilibrium. So what was discussed here, this is actually a discussion in Colson, is how the wet bulb temperature is being determined. Okay? Now, in problems that you will be encountering in drying, one of those is always having or associated with the time for drying. And when we speak of time for drying, it has something to do with both conditions. That is, you account for the constant rate period drying time and you account for the falling rate period drying time. The total drying time will be the time that is requested or that is required by the problem for you to determine. So if the material is dried by passing hot air over a surface which is initially wet, the rate of the drying curve in its simplest form is represented by these 3 points. Though it's being mentioned here to be a curve, now in our computation, the equation is not that of a curve but that of a line, comparable to that of the line, which has one part at times not being equal to the equation of a line. So in that case, we will just simplify it, or to simplify things, we will just account for the time based on this linear relationship. So one is this and the other one is this. So the falling rate period is this line, whereas the constant period or the constant rate period is a horizontal line. The relationship that was plotted here, class, is the rate in which the moisture content of the material is changing. So that's your dWdt divided by the cross-sectional area that is exposed during the drying period. Now, you have here the W1, the WC, and the WE representing the initial moisture content, the critical moisture content, and the equilibrium moisture content respectively. So what you have here on the horizontal axis is the total moisture, or rather the moisture content, because it could be any of these three, or it could be also total moisture, and this one, the rate of drying per unit area of the surface exposed during the drying process. Now, I have mentioned that it's comparable to an equation of a line. So for the for the time, for the constant rate period time, you have the formula omega 1 minus omega c over RC times A, or the product of RC and A. These omega actually are the W's that I have written in the previous slide. In Colson, they are represented as some form of a W, italized W. That is why I have written it here as omega. Now, you won't have, I think, a comparable representation of this. You will have a comparable representation of this in Jan Kupis also. But what I'm using here as a reference is Colson in this set of slide. Okay, so in here, you will be needing the two moisture content, the initial moisture content and the critical moisture content. And you will be needing the rate of drying per unit area. And most of the time, class, this is not given by the problem. Good if it is given. If it is not given, you can substitute RC by this. The mass of the material times the difference between the critical moisture content and the equilibrium moisture content of that particular material. That this product of these two can replace R sub C. Area is still the area of the exposed surface, knowing that this one is per unit area. Okay, as for the falling rate period, so that is why I'm saying that it's not really a line, it's curved, but it's represented as a line just for the case of simplifying something that is that would be difficult, because the formula here has an ln function, so it's not linear. But as how do we determine the falling rate period drying time, so it would be based on this formula. Anyway, we have already defined the W's, and the M is the mass of the material, and the W without any subscript is the total moisture content, which is actually the moisture content at any time t. The moisture content at any time t is W, or omega. So in determining the drying time, we need to get the sum of these two. This is the total drying time that is. So you need to get the sum of the two, and the resulting formula will be, of course, the sum of the two. I did not write it here anymore. If the problem is basing the computation on the free moisture content, or if what is given in the problem is based on a free moisture content data, then this is how you determine the free moisture content. So if it's the initial free moisture content, you just change the W here to W sub 1 minus W sub E. If it's the final moisture content, stipulating the time in which drying has already proceeded, then that would be W minus WE. So this is the generic representation. But this free moisture content formula could be at any condition. It could be initial, it could be final, or it could be somewhere, that the problem along the time of drying that the problem wants you to simply determine the free moisture content of the material. What do I mean by that? For example, if the total drying time is 10 hours, but the problem is asking you to determine the free moisture content at 5 hours, this would still be the same formula that you will use, as long as you know the moisture content after 5 hours. So if it's the initial free moisture content, then this would be W sub 1. So the W here could be any moisture content for any particular time t based on our definition. So moisture content for any particular time t. So this free moisture content could be any condition that is stated in the problem, initial, final, or in between the course of drying process. So we have here a sample problem to illustrate simply, because I have so far only discussed this particular formula for drying time. So we will just simply use it for now in this sample problem number 1. We need not think of any other formula to use, because so far that's only the thing that you can use, and that's the time for drying. So in here, you're given a wet solid which is dried from 25 to 10% moisture under constant drying condition. And it took it 15 kiloseconds, or that's 4.17 hours, to reach this particular moisture content from the initial, which is 25. If the critical and the equilibrium moisture contents are 15 and 5% respectively, how long will it take to dry the solid from 30 to 80% moisture under the same condition? Now, you have to understand, class, that in this problem, there was no mention about the falling rate period. This is only constant drying condition. So meaning, in the course of drying for this particular solid, there was no decrease and marked decrease in the value of this one. I'd like to show to you this one. Since it's constant, there is no marked decrease in the rate of drying per unit area. So it's a constant. So it's not always, class, that you will always find for the falling rate period and then add it to the constant rate period. If the problem is not mentioning about the constant rate period, then your drying for your particular material is just something that is continuous, meaning represented on this particular graph by a horizontal line, meaning that this one is not changing because you have a horizontal line. This is in the case wherein this one, the rate of drying per unit area is changing, or the rate in which moisture is decreasing per unit area is changing. So you have this falling rate period. The term falling rate meaning the rate is falling or decreasing. So let's go back to our problem. So this problem will simply be something that is constant drying. So there's no falling rate period in this case. Okay, so we need to write down our given for this problem. I'll stop share for now here. Go to the board. Okay, so for this particular problem, we'll start with what we are provided. So you'll be refreshed on what the problem provides you. So initially, the problem gives the initial moisture content to be equal to 0.25. So this is kilogram water per kilogram of material. So I will only write the unit here. For the rest, I will not write anymore because it's really difficult to write now on my board. Now, after some time, from this 25% moisture, it was decreased to 10%. So it's only 0.10. And it was stated that the equilibrium moisture content is 0.15. So it's still kilogram water per kilogram of material, and the critical moisture content is 5 or 0.05 kilogram of your water per kilogram of material. Now in here, for this constant rate period, because anyway, these two are constants, this is for, by the way, class, this is material. This is for a time equal to 15 kiloseconds. Okay, that's 15 kiloseconds. Now, in terms of determining the total drying time, so you are asked here to find the T, the total drying time for an initial moisture content of 0.30 to final moisture content of 0.08. Okay, though the problem is saying that the drying time is constant, when you solve for the total drying time, it should still use the time, total drying time, which is already accounting for the falling rate period time and the constant rate period time. Okay, even if the problem did not say that this one is for falling rate and this time is for constant rate, you still need to use the formula for the total drying time in this case. Now, I'd like to go to the next slide. So you need to get the sum of the two, which I presented on the slide. So in this case, that would be omega 1 minus omega C over R sub CA. If you notice, this one is for your constant drying rate, or this is for the constant rate drying time. And this one is for the falling rate drying time. So 1 over MA, and this one has the ln of omega C minus omega E omega minus omega E. And by the way, this problem is taken from Coulson because most of the board exams are actually taken from Coulson, especially on the case of drying. Now, so we will substitute the values that we have in this case, but if you think there is no mention about the rate, there was no rate that was mentioned in the problem. So in this case, we will change our rate here to the product of M and the omega C and the omega E difference, or that's the critical moisture content and the equilibrium moisture content. So when I substitute everything here, I will have 15, and I will have omega 1, which is 0.25, and your critical moisture content, which is 0.05, and I will, what's wrong? Okay, and your denominator will be the mass, and you have the critical moisture content, which is 15, and you have the equilibrium moisture content, which is 0.05. By the way, class, here on this one is critical moisture content. If it's critical moisture content, this should be 15, not the equilibrium moisture content. So this is 15. I. Now, I still do not know the A, so we'll place the A here. And we'll have 1 or plus 1 over, I do not know M, I do not know A as well. So ln of, then I will need to substitute everything that I know here. So this is 0.15 again for critical moisture content. Then you have equilibrium moisture content of 0.05. This is E, class E. And you have here the final moisture content, which is 10. And you have equilibrium moisture content, which is 0.05. Now, if you notice in all this class, you have the MA and MA here not known. So in this case, we will solve the constant MA. So I will have here 1 over MA being equal to, so this, since the first term has 1 over MA and this one has 1 over MA, you can factor 1 over MA and then process the sum of the factors that you have here concerning these two. The sum you will use as a divisor for 15 so that you will have the value of 1 over MA. So in this case, your 1 over MA is 8.859. So that is if you are going to get the value, simply factor out 1 over MA here, and then the rest are all constants which you can just transfer. So that's your 1 over MA. So the purpose of the first condition is for you to know the value of 1 over MA. That way, when you already make use of the second condition, this one in the unknown, this two, you will already know the constant 1 over MA that you will use in the same formula. So if we will do that, the T for the second condition will be, now I will have the 1 over MA factored. So you will have 1 over MA. For the first term, you will have your initial moisture content minus the critical moisture content, and the denominator, which is your critical moisture content minus the equilibrium moisture content, which is 0.05. Okay, where am I getting this? It's here, class. So if you'll take out the 1 over MA here, 1 over MA, what is left is omega 1 minus omega C over omega C minus omega A, because you have factored out MA in the denominator, or specifically 1 over MA. You do the same here, so your second term will be left only with the ln term. So what is left here on the second term is just your ln term. So the ln of, again, those moisture content. So we have the critical moisture content, I have problem writing, minus the equilibrium moisture content, and then with the denominator, this is your final moisture content on the second condition, again minus the equilibrium moisture content. Okay, so sorry class. So in here, you will be getting a value for the T. If you will substitute the 1 over MA of 8 point, how much was that? 8.859, the one that we got using the first condition, you will have a new drying time at the new condition of 23.95 kiloseconds. Now, true that if you need to validate this one, it's acceptable because the original moisture content is 25 to 10. You need to lower the moisture content to 10 from 25. Whereas the one required starts with a higher initial moisture content and even ends with a much lesser moisture content than the original condition that was stated. This one is 10, whereas this one is only 0.08. So we expect a drying time which should be higher than 15 kiloseconds. So in this case, your drying time is 23.95 seconds. So this is already our answer for this particular problem. The total drying time based on the new percentage moisture and the value in which it is going to decrease to. Now I will go back to our slide and proceed to the second sample problem. So this is our this is our second sample problem. If I'll get disconnected, we just return using the same link. You're given here a wet solid which is dried from 25 to 10% moisture under constant drying condition for a period of 15 kiloseconds. Oh, sorry, this is still my problem number 1. So let's go to problem number 2. Now, problem number 2 concerns strips of material 10 mm thick, which is to be dried under constant drying condition. So, constant drying condition, this implies that the condition for pressure and temperature is fixed from 28 to 13% moisture for a duration of 7 hours, or that's 25 kiloseconds. If the equilibrium moisture content is 7%, what is the time taken to dry the same plank, but however, it's thicker? So this one, it's 60 mm planks, and it will have to start from an initial moisture content of 22, and it will have to decrease to 10, the moisture content that is, under the same condition in which the first material was subjected to. We are to assume that no loss from the edges during drying will occur. By the way, in the course of drying class, it is assumed that if your drying medium is passing parallel to a particular face of the particular material, we are assuming that the drying on the sides are negligible compared to the rate of drying on the exposed surface. So this is what the problem is saying here. Under the same condition, assuming no loss from the edges. Now, all moistures are given on a wet basis, meaning total moisture content plus the material that is. So, the relation between the E here is defined as this, the ratio of the average free moisture content at time T to the initial free moisture content, this E. So, meaning the free moisture content at any time over the free moisture content initially. So, this is the E that is written here on the first row data. And it is to be plotted against the parameter J. So, the parameter J is defined by the formula KT divided by L squared, where K is a constant, T is the time in kiloseconds, and L is half of the thickness of the sheet of material. And by the way, this formula class is only true for this particular problem, true for the given condition. So you are in this case to determine, oh, sorry. So you are to determine the drying time if your material now, which was originally only 10 mm thick and initially with 28% moisture, lowered down to 13%, will be 60 mm thick, and it will be dried on this particular percentage moisture, initial 22 to 10%. And you are going to use this particular data. So whenever class you're given a data in a problem, you are to think what is the purpose of that particular data that is given in the first place. This one gives you a relationship between the ratio, that is E, that is defined here, and the J, which is this KT over L squared. So what we're going to do in this case is plot this particular relationship. And if it's plotted, it would look something like this. The one that I have shown a while ago, this one. So it's actually, it has to be a smooth curve. So what I have here is a crude curve, but that's how it's going to look. Now, your problem will be part graphical, part analytical, because we will be relying on this particular graph that we have for E versus J in this case. Now, what do we need to determine in this case so that we can use this graph and from this graph also arrive at the answer that the problem requires from us? If you recall, I have really emphasized the use of the free moisture content formula a while ago. So we will be using that particular formula in tackling this particular problem. So I'll go to our board. And first, we'll write down the given in this problem. So case 1, same material, the thickness is